Our guest speaker this week is Dr. Madison Borrelli, who's a planetary geologist and postdoc at Georgia Tech. Her research has mainly focused on studying volcanic and impact processes to gain information about the exterior crust of planetary bodies. She has studied several planetary bodies, including Venus, Mars, and Uranian satellites, which she's going to be talking about today. And I think that's Miranda and Ariel, right? And she has a bachelor's in physics from Wheaton College, and then a PhD in geosciences from ASU, where she defended a couple of months ago. And she just moved here. She lives in Athens and then travels here every so often. And so she came from Athens today to talk to you all. And so welcome to speaker. Thanks again.
Thank you. Thank you for having me. As Francis said, I just started recently as a postdoc here. I'm working with Dr. Induja Ganesh and focusing mainly on Venus. But I know everyone heard about Venus recently. And so I wanted to talk about something a little different, which is work that I did on a couple of the Uranian satellites. So we can get started. First, I'm going to clarify what I mean when I say Uranian satellites, because Uranus has 28 known moons. Most of them are ring moons, which are very, very small, but it has 5 classical satellites. They're also called the literary moons. They're named after Shakespeare characters. They are outside of the rings. They are the main satellites that we're going to talk about today. So the Uranian satellites are particularly interesting, especially from an astrobiology perspective, because they are icy bodies and they are potential ocean worlds. They have really rich and active geologic histories that are recorded on their surfaces. So we all know, the search for life often begins with the search for liquid water. So the Uranian satellites are some really good targets for astrobiology missions. It's also important that we study them now, since the most recent decadal survey identified the Uranus orbiter and probe as the top priority for the next NASA flagship mission, which is the largest COSMOS mission. So it's going to be super exciting when we have some great data of these moons. So actually, I am only focusing on 2 of these moons in my work, Ariel and Miranda. Basically, the data is higher resolution for these 2 moons than it is for the other 3. The data was also recently reprocessed by Schenck and Moore in 2020, which really enabled this type of crater study that I'm going to get into. I would definitely have loved to expand this study to the other 3 major satellites. However, the data is just not up to that standard yet to allow meaningful estimates. So that's kind of going to be a theme for this talk as well. It would be so great to do more on the Uranian satellites someday when we have better data. But it's not all bad news. Ariel and Miranda are especially cool, so happy to focus on these 2. Miranda has these 3 visible features called corona. If you're familiar with Venus, Venus also has corona, but they're a totally different type of feature. It's the same exact word, but it basically just means like oval shaped thing, and is a completely different feature on Miranda. They are these oval to trapezoid shaped features that are really highly deformed. There are these 3 kind of wrinkly looking areas. We don't have coverage over the entirety of these 3 corona, but what we do see, it's definitely intriguing looking. There's different theories about how they formed. It's still an open question. Maybe some hypotheses are that they formed by upwelling material and tectonic activity. Maybe it was downwelling from an impact or breakup and reaccretion, or they could be extensional features. definitely the topic of a lot of research is the corona. On Ariel, we have some standout features as well. Ariel has these really large canyons called chasmata, which are 3 to 4 kilometers deep and hundreds of kilometers long. And some of them have evidence of lithospheric flexure, which is a really valuable tool. Actually, a lot of my research is focused on lithospheric flexure, but just not on these moons, mostly on Venus. But you can use that as a way to constrain the elastic thickness and the surface heat flow at those locations. So there's definitely research on these really cool canyons on Ariel. But the Uranian satellites were imaged by Voyager in the 1980s. It's been 38 years, so why now? As I mentioned, the data was reprocessed a few years ago and kind of makes what's old new again and allows us to revisit some previous studies. And in the last 38 years, we have developed a lot of new techniques and technologies. So with modern GIS techniques, it makes these crater counting studies far, far easier. And especially, we have learned so much about icy bodies since Voyager visited the Uranian system. So we have really incredible data of other icy bodies in the solar system, like the Cassini images of Enceladus and the New Horizons data of Charon and the Dawn mission at Ceres. And so this has enabled us to learn so much about ice rheology, crater counts. We could get ages, we can learn about their surface composition. We've learned about crater relaxation and transition diameters in the past few decades. So I really wanted to use these lessons that we have learned from across the solar system and apply them to Ariel and Miranda to the extent that the data will allow. So some background about the data that we have. The Uranian system was visited by Voyager 2. It flew by, made its closest approach, and imaged the satellites in January of 1986. It observed Ariel from 80,000 miles away, Miranda from 18,000 miles away. And the way that the Uranian system was oriented at the time of this flyby, Uranus orbits on its side and Voyager flew by, and it was like looking at a bullseye with Uranus in the center and the rings and the moons around it. So we only have imagery over the southern hemisphere of all of these moons. And actually, we really only have coverage of up to about a third of some of these moons. So there could be absolutely anything on the other hemisphere. We simply don't know. We have a 9-image mosaic of Miranda, 4 images of Ariel, and 1 of the rest. The data resolution, we've got on Ariel about 1 kilometer per pixel, Miranda 250 meters per pixel, and the rest kind of range from about 3 to 5 kilometers per pixel, which I think is kind of a fun contrast to the seminar last week about Mars, where I think I heard the phrase centimeters per pixel. And I was like, oh my God, that's amazing. So this is what we're working with here. To put this in perspective, here is some explanation of why we're looking at only Ariel and Miranda. The scale bar is the same on all of these images. This is about a 15 to 20 kilometer across crater, what I think is a crater, on some of the larger 3. And on Miranda, it's honestly, I feel so spoiled with 250 meters per pixel. But the type of crater counting that I was doing, I really needed about 5 pixels across to have accurate counts, and especially when I'm using the topography of these craters. So there is a diameter cutoff certainly for what I can measure, and definitely felt that only the smaller 2 would lead to meaningful results. So I conducted 2 different types of crater studies on Ariel and Miranda to determine the ages of a few different surfaces and the transition diameter. So wanted to revisit them with the newly processed data and see, what we could find. And this definitely tested the limits of the available data. So based on this experience, we make some recommendations about data resolution for future missions and how that can improve studies like this one. So my study area on Ariel is outlined here in yellow. I have one study area, which is consistent with a previous study of crater ages and transition diameter on Ariel. Whereas on Miranda, I break the study area into two different regions because it has such distinct morphologies. So in red, I've outlined the study area that encompasses Elsinore Corona. And in blue, I've outlined the study area that encompasses mostly the smooth plains. I call it the smooth middle region. Yeah, so those are the study areas. So I did a bunch of crater counts, drew so many circles, and categorized them all into these two categories as simple or complex. So simple craters, here's an example, they are bowl-shaped, and complex craters have additional topography. There could be several different types of topography that make a crater complex. In my case, I looked only for the presence of central peaks. On Ariel, I didn't find evidence of other types of topography, but complex craters could also have rings of peaks. They could have scalloped rims or terraced walls. But in our case, we look for the central peaks. Complex craters are also generally larger than simple craters. And the reason is that how they form is when you get to a certain diameter, that bowl shape is not stable and it will collapse. And so the diameter at which a crater is more likely to be complex than simple is the transition diameter. It's a really valuable tool. You can use that to as a proxy for surface strength. So a weaker surface, like an icy body, will that collapse is going to happen more readily, and you'll have a lower transition diameter than on a stronger surface, like a rocky body. It's also inversely related to surface gravity. On a body with stronger surface gravity, as that collapses again is going to happen easier, and you'll have a lower transition diameter. So some of the craters were not really able to be confidently characterized as either simple or complex. Here's an example of where we ran into some limitations with the data. Luckily, there weren't too many where this was the case, where we categorized them as uncertain. And the uncertain craters are not part of the statistics that we do later on. But I just wanted to show you one that doesn't look as crisp as the other two. So we categorize this as an uncertain complex crater in the red line. So I take 4 topographic profiles over each crater, and the red line looks like it has a central peak, but that's only 1 pixel. And it's really pretty much just visible in that, that profile. So some of them, we don't feel like we can really make a judgment with the available resolution. But Ariel's transition diameter has been measured before. Paul Schenk measured the transition diameter in 1989 using the original Voyager data. He used a couple different methods to do so, but using the method that's most similar to the one that I used, he found a transition diameter of about 15 plus or minus 5 kilometers using a data set of only 18 craters. And this was definitely worth revisiting since the new data and the newly processed data and the new techniques enabled us to conduct the study with a data set of over 100 craters. So this is one method of determining the transition diameter. It's called the intercept method. This method relies on you measuring the depth of the craters. So you plot the depth versus diameter of all of the simple craters and all of the complex craters, of which they're in pink. You can see there's not that many complex craters. And you plot a best fit line between each data set. And the point where those 2 lines intersect is the transition diameter. But importantly, The dashed lines here are the 95% confidence intervals of those best fit lines. And both of the lines are completely within both of the confidence intervals. So really, these slopes are indeterminate. They're indistinguishable. So the intersect point could kind of be anywhere along that lines. So the intercept method is not reliable with the available data. However, there are other methods that you can use to get a transition diameter. This is the morphology method. This is the method that we ended up using. You can treat every single crater as a Gaussian distribution. You plot the likelihood of each crater across the full range of diameters. And the point where complex craters reach and maintain at least 50% probability is the transition diameter, which I pointed out, the black arrow here. So using this method, I found a transition diameter on Ariel of 26 kilometers. On Miranda, we're not really able to estimate the transition diameter. There is one crater on Miranda that is maybe complex. It definitely has, some fractures and other interfering topography. So makes it hard to definitely say, oh, this is certainly a complex crater because it seems pretty old and there's a lot of other stuff that we're catching when we do these topographic profiles. Plus, one crater is not doesn't make awesome statistics. So instead, we can only say that there's a lower limit on Miranda's transition diameter of this diameter, about 49 kilometers. There are a couple reasons why we might not be seeing complex craters on Miranda. Maybe they aren't there. Maybe they are there, but they're on the other hemisphere, and we'll see them someday. Miranda could have too low surface gravity to even form complex craters, where the transition diameter would be so huge that an impact of that size would just destroy Miranda. It is also hypothesized that Miranda has a really thick layer of regolith, potentially the thickest in the solar system, and that could be mantling these craters and hiding evidence of central peaks. So I mentioned that the intercept method relies on you determining the depth of craters, which might be like, oh yeah, okay, I'll just get the depth. But there's comparisons of transition diameter can be really difficult. There's so many different methods and differences in reporting of methods that really make these kind of tough. So I just like to point out this really great paper about measuring crater depth through the solar system. There's so many different ways. So they do a huge literature review of crater depths across all different types of bodies. People are doing it all different ways and they're reporting it to varying levels of detail. So when you are relying on crater depth measurements to conduct your transition diameter study, you definitely want to take into consideration how these depths are being measured, how you are measuring them in relation to other people. And also all the things that can happen that affect a crater's depth after the fact. So I love these figures from Bedingfield and Cartwright, where they compare a fresh crater with craters that have been affected later on by a few different processes. And I mentioned mantling of craters that could be happening on Miranda. We definitely see a lot of muted craters. And these processes like that can impact your measurements of their depth and diameter. Depth diameter measurements on their own are also a really valuable way to learn about craters. If your depth diameter is not what you would expect it to be for a fresh crater, maybe that's evidence that some of these things are happening. But when we're looking for a transition diameter, it can kind of interfere with our comparisons across different bodies. But we still want to do these comparisons. So just to put our estimates in context, I compare them to estimates of transition diameter across the solar system. So I think it's really important to note that you really only want to compare your estimate to those that are measured using the most similar method that you can. So I have the intercept method and the morphology method split up. You can see a couple of the trends here. So I have the rocky bodies in pink and the icy bodies in green. And you can see how they are inversely related to the surface gravity. And the rocky bodies have the higher transition diameter. I did not use the intercept method, so my results are here on this side, the morphology method. You can see them in context. Also, definitely want to note that in comparing these results and for different methods, the morphology method generally leads to higher transition diameter estimates than the intercept method, just as a whole. So when looking at transition diameters, just something that you always want to keep in mind. And what we can learn from our estimates is about the surface strength. So if we extrapolate from the trend for icy bodies, given its surface gravity, we would expect Ariel to have a transition diameter of 16 kilometers if it were primarily icy. And extrapolating from the trend from rocky bodies, we would expect Ariel to have a transition diameter of 41 kilometers if it were primarily rocky. So my estimate of 26 kilometers is more closely aligned with the icy body trend and is consistent with Ariel being a differentiated body whose surface is primarily icy. So we also wanted to do some age estimates. So everyone here is probably familiar with crater age dating, but I'm going to like go over it just in case. So I'd rather run through it. So say you have these two surfaces on a planet. Everything is the same. They're the same surface area. And over time, stuff is going to come and it's going to slam into it and it's going to make craters. And eventually, one of these is the slate is wiped clean. We don't know what happened. Maybe it was a volcanic event. Maybe it was an icy body and the surface melted and refroze. We don't have to know what happened, but something happened and erased all the craters that used to be there in this area. And then more time passes and things come and impactors hit it and craters are formed. And then you can look at these two different areas and see that the one on the right has more craters than the one on the left, all else being the same. That surface is older. It's had more time to accumulate craters. So with this in mind, let's revisit the study area on Miranda. So we've got Elsinore Corona and the smooth middle region. Just looking at it, you can tell that the smooth middle region has more craters. It's also a larger surface area, so we do have to correct for that. But it's got a higher density of craters than Elsinore Corona. They're not all super crisp and really nice looking like these on Elsinore Corona, but part of it is the lighting of the imagery, and part of it is that a lot of Miranda's craters, like I mentioned, are potentially muted and mantled, but there's so many on the smooth middle region, we'd expect that to be older. So we test this. We plot our cumulative size frequency distributions, which is the craters at every given size and its density for all three of the study regions. And the Miranda Plains region in the light green consistently has a higher crater density than either of our other study regions. So that is the oldest of the three study regions. So we can say we can get a relative age using the size frequency distribution here. Ariel and Elsinore Corona are both younger than that, so they must have been resurfaced at some point, which makes sense. This is definitely consistent with the idea that Elsinore Corona and all the corona are highly deformed features that experienced some sort of major event. But we can say one is older than the other, but if we want to actually know how old is it and get an absolute age, we have to use a production function. So I specifically use the production function from Zonali et al. 2003, which uses impactor populations from Triton and Jupiter. And a production function is a model that tells you, given an impactor population, how many craters would you expect to form over different amounts of time? And you can compare that to the measured crater size frequency distributions. So the same plots of size frequency distribution are here in the black dots. And I compare them to the model and we see what's the best fit. So for Elsinore Corona, it's most similar to that orange line. For Miranda Smooth Middle, it's most similar to this light blue. So we can say that Elsinore Corona is about 1 billion years old and the Smooth Middle region is about 3 billion years old. The study area on Ariel is the youngest of the three that I looked at, and we found that it's about 0.4 billion years old. So this is kind of the conclusions of my study. I know I was mentioning the data so much, but it's really great that there's still so much we can do with this 38-year-old imagery. We have just 4 photos, and there's so many things that can be used for it. So I found that Ariel's transition diameter is consistent with a differentiated, primarily icy surface, and that both Ariel and Miranda underwent relatively recent resurfacing, which is definitely exciting. You know, maybe they had elevated heat flows. These are things that we really want to learn more about if we are to determine whether or not these are ocean worlds. So I've talked so much about the data, but just another example of a crater. In the paper, I call this the rogues gallery of the uncertain craters, where there's some of them where it's just like, what? But what we want to do is, we know that there's going to be a mission, hopefully someday, and what is the best way to improve this study? Every single aspect of the study would be improved by a higher resolution data, but how high? So ideally, a future mission would collect coverage over both hemispheres for both imagery and topography. In getting especially the depth measurements, the topography is either not available everywhere at all or not available at high enough resolution to conduct this study. So global coverage of all 5 major Uranian satellites would be ideal. And my recommendation is 300 meter per pixel imagery, 200 meter vertical precision DEM. That would be most useful for estimates of transition diameter. And for better age estimates, ideally all 5 of the Uranian satellites would have imagery of at least 250 meters per pixel, which is what we currently have on Miranda. So if we could have universal data of the same resolution on Miranda, that would be definitely really huge. There's a couple other things that craters can be used for that I do want to cover. So I have my study area on Ariel outlined again, but I've highlighted Ariel's 2 largest craters, Yangor in pink and Domovoy in blue. And they're both clearly identifiable in the imagery. They're very close to each other. They're at a similar latitude, and they're of a relatively similar size. However, in the topography, Domovoy is clearly identifiable as, relatively bowl-shaped and deep, but Yangor is relaxed. It's got this really jagged topography. The rims of that crater are pointed out with the black arrows. And the highest point is actually the central peak. It rises above the surrounding topography, which is evidence of viscous relaxation. So that means that something would have happened to relax this crater after the formation of Yangor, but before the formation of Domovoy. And it begs the question, how high was the heat flow that would have been capable of doing this? Is that heat flow sufficient to have created an ocean on Ariel? So there has been some modeling work on this. So Bland et al. 2023 conducted a relaxation model where they took a deep crater, a Yangor-like crater pre-relaxation, and determined how high would you need the heat flow to be under different conditions of porosity and composition to lead to the relaxation we see today. And they found that the heat flow would have had to be 30 to 60 milliwatts per meter squared to be capable of relaxing a crater of this size. Radiogenic heating alone on Ariel would only produce about 6 milliwatts per meter squared. So there would need to be an additional heat source, probably tidal heating. Yangor crater is also about 300 kilometers away from other features where high heat flow has been measured. So we don't know if this would really be truly a global high heat flow, but certainly not extremely localized. So that's exciting stuff in the realm of, is there an ocean on Ariel? But it doesn't stop at just Ariel and Miranda. The other Uranian satellites could very well be ocean worlds. For example, some thermal modeling by Pearson and Nimmo found that Titania could actually be able to sustain a liquid ocean up until the present day. So things that are really exciting when we look forward to the Uranus orbiter and probe. The mission concept study for the orbiter and probe identified these questions in relation to the satellites. So what are the rock to ice ratios? Do they have internal heat sources? Can we constrain their formation and evolution with their compositions? What processes do the surfaces record? Can we learn about impactor populations? So I hope you feel that we touched on some of these things today. Now is really a great time to get involved with the Uranus satellite research to kind of lay the groundwork for working towards answering these questions. You know, the more we learn now, the more we'll be able to do with available data when it comes to us. If you want to read more about it, you can check out my preprint. It should be available in JGR Planet soon. Yeah, happy to answer any questions. Thanks.